I think Dr. Kristen Grauman is here. I can see her.
Yes, I'm here. Hello.
Okay. It's my great pleasure to introduce Dr. Kristen Grauman. And Dr. Grauman is a professor in UT Austin and a research scientist in Facebook AI research. And her research on visual recognition and search is well known within the community, and especially for the work of pyramid mesh kernel, hashing algorithm for large-scale image retrieval, relative visual attributes, which has won Computer Vision Test of Time Award, CVPR Best Student Paper Award, and the MAR Prize. Her incredible research has been recognized by many other awards, like Microsoft Research New Faculty Fellow and the NSF Career Award, ONR Young Investigator Award, and the Presidential Early Career Award, Hami Young Investigator Award, and the Shichao Computer and Thought Award. And she is also IEEE Fellow, IEEE Fellow, and Sloan Fellow. One special award, UT Academy of Distinguished Teachers, recognized her outstanding teaching effort. Even myself was influenced by her teaching in a very intensive one-week class that raised my interest in computer vision back to almost 10 years ago. And even right now, when I teach computer vision classes, for some concepts I don't know how to explain, I go back to see the slides that Kristen explains that. I believe many of the audience here will benefit from her talk today, like me. So I will let Kristen begin her talk. Thank you.
Hi, I'm Kristen Grauman. I'll be talking about audio-visual navigation. And this is a project that's done with a number of collaborators that you see here from Facebook AI Research, Facebook Reality Labs, and UT Austin. So to set the stage, we are thinking of problems with embodied agents that are learning how to move around even in unmapped spaces. So we want agents that can, for example, enter a new Airbnb and just by the looks of what it sees from an RGB image, start to have intelligent motion decisions about where to go in order to answer questions like, where would a telephone likely be? Where do you think the TV sits? Or how could I get to a given displacement within this environment, given that it's unmapped? And we've seen a lot of very exciting work in the community happening around this challenge. Problems like visual navigation and visual exploration, where you can have systems learning from the bottom up, even how to map the space and how to encode not just where things are, but also semantics that help an agent intelligently move. Now, at the same time, there's a salient missing ingredient for these agents. They live in silent environments and they are deaf. And so this is the thing that I want to zero in on in this work, looking at how to instead consider the world as an audio-visual place for our agents, and in particular in the context of navigation. So why do we want to do this? What will sound inform our agents about? There are a number of different important things that we can expect. One, it will allow an agent to hear something that is itself the target. For example, the phone ringing in another room, or the baby crying, or some window breaking. This is something the agent should be able to move to even though it can't see it yet. There's also possibilities for safety, like places that should be avoided based on the sounds that are coming from them, or other dynamic object occurrences. Furthermore, we have semantics and sound. If the agent at the bottom of this scene were to hear water running from a given direction, that's a sign about what possible objects or scenes or rooms might be there. And finally, sound gives us information about geometry and materials. So knowing what we can hear and understanding the link to spatial characteristics of the environment gives us a richer perception in our, for this audiovisual observation. So I am going to touch on a few of these cases in this talk today, and starting with the one of audio goal. This is where, say, there's the phone ringing in another room and the agent needs to navigate to it. And what's really important to notice about this challenge is that the audio is going to allow us to sense the target before we can actually see it. For example, here on the right, if the phone is near that couch and the agent is down outside of both of those rooms, but can sense the sound intensity coming and bleeding through the doorway, this will be a sign signal that we should be able to learn to send the agent to the proper place. Now, this is the first time to our knowledge that this problem has been tackled for agents working in photorealistic environments with 3D settings and real sound. So to do this, we first needed to establish an audio simulation platform. We want to be able to hear proper sounds for our agent as a function of the geometry and materials of the environment. So to do this, we started with the publicly available replica environments, like one that you see here, and we used an audio ray tracing approach in order to render and pre-compute the sounds for all parts of this environment. In particular, you store the room impulse response for every source and receiver coupling of locations. And that's what these yellow positions are here in this environment, places at which there would be room impulse responses measured. Now this RIR is the transfer function saying how sound is transferred from the source to the receiver as a function of the geometry, as a function of their relative separation, and a function of the materials in the space. Now, once we have these functions, we can convolve with the appropriate one in order to hear the agent's sound at any given position for any given source. So for example, here, if the source was at that red hotspot, then the agent would receive the appropriate binaural sound when we pull it from the given receiver location anywhere else. Okay, so this is a general rendering of the sounds now computed for all. Now let's look at the task. Here I'm going to play a video and we're going to hear the sound and see what the agent sees on the left-hand view. The top-down map in the center, not available to the agent, but it will start to discover it as it moves. There's a phone ringing, it's coming from another room, and the agent's job is to go find it. And you can see as the trajectory goes that the agent could tell as it exited that first room that it wasn't in that direction. And then as it moves down closer, it'll start to hear that the phone is getting louder, and furthermore that it's coming from the left side. Now keep in mind, to hear this, you'd need to listen to our original video with headphones. And so then it approaches the target and it reaches it and stops. This is the task of audiovisual navigation: find the sound source and use both sight and sound to navigate to it. So the first model that we propose to tackle this problem takes a reinforcement learning-based approach in which we'll learn a policy for how the agent needs to move given what it's hearing and seeing from these multimodal inputs. And this framework is very much related to others that are now common for treating purely visual navigation. And it looks like this. So we have as input the visual stream, and then we also have, in our case, this audio stream, which is coming as input in terms of two spectrograms, one for the left ear, one for the right ear, and optionally there will be GPS sensing. Now the multimodal inputs are aggregated over time with this sequential model, and we use an actor-critic approach for learning this policy in order to generate actions that the agent will take. And these are actions in the space of move forward, turn left, turn right, stop. Okay, and having sampled an action, then this loops back because the environment changes, the agent sees and hears something different as a function of its movement. And what it'll learn is, by us rewarding it for navigating quickly to the target, it will learn a policy to use all these cues in order to find this sounding object. Now, importantly, we consider both the case with all three of these modalities, as well as the case where, in fact, the task is simply audio goal, meaning there's no pointer at the onset, like in the so-called point goal task, telling us where the target is. And I'll come back to that in the results. So first, let's look at what the audio features learned within this model have captured. These are T-SNE plots showing projections in 2D down from the CNN encodings that were learned for those spectrograms. And on the left, they're color-coded according to the distance to goal, and on the right, they're color-coded according to the angle to goal, which of course is not directly known by the agent, but what we see here is that, as exhibited by the clustering of similar colors, meaning similar distances or angles in these plots, that the features learned have managed to capture this automatically. Now, what about actually executing on some episodes of navigation? Here, I'll first show you an example, and then we'll look at some numbers. So here is a baseline. This is a point goal agent that does not have sound, and is trying to navigate to the target, which is yellow on the bottom of the screen, using just vision as well as GPS. And what happened in this particular case is, though, while there's a shortest path there in pink that would require going outside the door and then around to the other room, the agent ran out of time in this episode, kind of stumbling around at that bottom mid-wall. And that's because the point goal signal from the onset was telling it very strongly to go in that direction to get to the yellow target. And this will give you the kind of success rates you see here. This is the success rate normalized by path length, or FPL, the common metric for navigation, and higher is better. Now, if instead we use our agent and treat this as the audio point goal problem, where we do get that pointer towards the goal in this case, but we also can hear that sounding target, we get a much closer path to the shortest path. And the numbers as well go up significantly. So this is great news, as we would hope once we are incorporating audio into the framework as part of the sensing to find this goal, the accuracy of the navigation is much better. The next thing I want to show you, we think is even more than that. So here, when we treat this task of point goal or audio point goal, we're saying that at the onset, the agent has a vector telling it where is the goal. And this is very commonly the way the task is posed in the navigation literature today. However, we also know that having that information is extra, right? And furthermore, if we rely so much on that information to get us there in combination with a GPS sensor, we'll be in trouble if the GPS is not perfect. And so what this chart does is look at success rate on the vertical axis as a function of adding more and more noise to the GPS sensing. And first of all, what you see here is the good news that because our agent with audio can still hear even in the presence of noisier GPS, its accuracy rate stays relatively stable as that GPS gets noisier. So this is important. Furthermore, if we think about the task, which is audio goal, meaning we do not get that displacement vector at the onset telling us where is the goal, then in this different task, we can still be completely immune to any problems with GPS. In fact, we're not using it, right? So the agent is able to find its way to the goal at a steady accuracy rate without needing this direct pointer to it. And I think this is an important suggestion about where audio can play a role for this real-world task of moving towards sounding objects. And by the way, even if we do add noise to the audio stream, we're seeing relative robustness to that. Now, in every case, the environment that the agent sees during navigation is new. Now, we're also interested in seeing what happens if the sounds are new. So this is a set of experiments where from left to right, we made more and more challenging sounds in terms of whether the agent had heard them during training or not. And the short story is that if GPS is also available, the performance is quite stable with respect to unheard sounds. If it's not, it does get more challenging. And I think we can improve these quite a bit once we're training on a much wider array of sounds. Now, the model doesn't always work, of course, and some of the failures we notice are things like you see here, where the agent may start oscillating around an obstacle or choose a path that is kind of a long way around it. And we can attribute this to a couple things about the current model. One, this action space is very step-by-step, and so there's a lack of abstraction or sort of myopic choices are being made. That's hard to do in a very long string of actions. And secondly, we have a memory that's rather simplistic so far, simply aggregating state through this GRU. So, in our next steps in this research, we've looked at how to overcome these limitations and really enhance the model that we're putting forth to do audiovisual navigation. And there's two important things in this new model. So in this picture, on the right-hand side, you can see occupancy map, acoustic map. Now these are new grounded spatial representations that we add to the model beyond what I was showing before, which is the egocentric view and RGB or the binaural audio spectrograms. And this will give us a multimodal spatial memory in which we record as the agent moves in this space, both where obstacles are in its occupancy map, but also the history of what it's heard as it was moving in different positions, what we call the acoustic map. So that's the one key new ingredient that we want to explore. And the other that we propose is audiovisual waypoints. So we'll make this architecture more modular so that we're not confined to these step-by-step actions of the agent as before, but instead the agent can set for itself waypoints that it should travel to with, in our case then, a planner to get to each intermediate point. Okay, so we're going to learn audiovisual waypoints, and we're going to incorporate an acoustic memory to make this model much richer. So let me show you what the model looks like then. Now we have as input the RGBD, so here we'll take the depth image, project down to the ground plane, so that as we accumulate these observations from the egocentric view, we get more and more of the occupancy map filled in. Secondly, we have the audio input, and now rather than only using those raw spectrograms for learning that you see on the left, we'll also have this spatially grounded acoustic map, which in this case is encoding the audio intensity at the egocentric positions and accumulating those over time in concert with the occupancy map. Then we'll have this important module which does the audiovisual waypoint prediction. And so now this policy is generating the waypoint. Okay, so given the maps that it's discovered so far, as well as the raw visual and audio inputs, it will select for itself a sub-goal. And if intuitively, as some of my images before showed, audio is strong as a sub-goal creator because, again, before we get to see something, we can hear it coming from certain directions, which suggests the kind of intermediate goals that might be useful to set. So in fact, we're going to learn to set these goals end-to-end within the navigation policy itself, or for the navigation task. And so having selected a waypoint, then the inner module of the system will plan a path given the partial map that's been reconstructed so far by the agent in order to meet and find that waypoint. Then the environment will update and the agent will see something new, hear something new, and this process continues. So the key new ideas in terms of the technical approach here is first that we're inferring sub-goals via the policy. And we think that this is new with or without the context of audio-visual. Traditionally, sub-goals are set in this navigation space based on intersecting the intended goal with the frontier of exploration, or by learning to map to shortest path waypoints. And instead, we're letting the policy learn to set these goals. And then the second key idea is the acoustic memory. Right, so let's look at what this, how this looks and sounds for an agent now, exploring another space. And when I play this, again, the goal is in the red, the agent's this blue arrow, and as we go, it'll set waypoints for itself in yellow, and the purple will illustrate the acoustic memory. So let's play this example. So it's starting to record its audio history in the acoustic memory. The yellow is the waypoint that it's setting for itself next. Phone is getting louder, the new waypoint set near that doorway. Entered the correct room, it's louder, the waypoints are getting closer. Okay, and then once the waypoint gives back a delta x, delta y, that's 0, 0, the agent will know it has reached, believe it has reached the goal, and will issue the stop action. So this was just one sample showing the agent at work, leveraging this grounded, spatially grounded acoustic memory together with its ability to set waypoints on its own, directly in concert with this navigation task. And we found quite good results when doing this. So here I'm reporting results on those same replica environments from before. And here are an array of metrics. SPL is the first column there. The others are success rate, normalized distance to goal, the number of actions, and the success rate weighted by the number of actions. And our result for a full model is shown here, highlighted in yellow, whereas the model of the previous version of our method that I described earlier is shown here in blue. You can see right away these new additions of automatically learned waypoints as well as the richer acoustic memory are responsible for a big jump in the success rate and the SPL. Furthermore, there's also some concurrent work coming at ICRA 2020 from Gan and colleagues, where the audio and the visual streams are treated separately, and the audio gives a beacon from which to predict the final goal location, and then the visual stream is used to navigate and plan to it. And we're seeing good results with respect to both these existing methods. Furthermore, you can see the impact of the acoustic memory in the ablation on the bottom, where the model here, ours AV WAN, without the acoustic map, AT, loses about 4 points in SPL. Now, to give a qualitative sense of what these agents are doing, the three I was highlighting on the previous slide, we can see example trajectories here. Now, remember that each of these agents has no pointer to the goal. They do have clean odometry, but there's no pointer given to know where the goal is. And we see on the left, with Jana and colleagues' approach, there's quite a challenge because the method requires predicting where the final goal location is based on audio and then navigating to it with the visual map. But this, because of the difficulty of finding that final goal prediction correctly, there's a lot of backtracking. In the middle, our previous model with pure RL and the step-by-step actions is better, but still doing some unnecessary motions thanks to that more myopic view of the action space. And then finally, the current model I've just described with waypoints is getting a much more efficient path on the right. All right, so I've been talking about this problem of audiovisual navigation with a target location, the ringing phone. And now I want to shift to an example from our work, trying to tackle the use of audio in a 3D space for semantics and geometry. And for this, we'll introduce our work on visual echoes. This is work done with the people that you see here, led by Rohan Gao. Now, we've been looking so far thinking about audio as something the agent hears from a distance. You know, there's some sounding object and it experiences it. Now I want to shift to the flip side, where the agent itself is emitting a sound in order to learn about the surrounding environment. So what will happen is the agent's going to emit a sound, and when it does so, then the environment will bring sounds back to it in terms of the echoes. And this is what we want our agent to exploit in order to learn about the geometry of the space. Where are the major surfaces? How are they oriented? Okay, so this is the main idea, and what we're headed towards is a new self-supervised image feature learning approach that is trained based on how an agent can learn the connection between what it sees and what it hears from echoes. So we'll return to the simulator that I described from our work earlier today. And in this now, we'll let the source and the receiver be at the same position. So the agent is somewhere in this environment and it emits a sound and also listens to the response at that position. And we'll emit a sweep of frequencies in order to get a rich response from the environment. Furthermore, we record these echoes from the agent's point of view. It moves in a few different orientations. So here we're looking on the left at a top-down view of an apartment. The agent is at that crosshair arrows, and if it looks in a certain direction, say forward, it will see the RGB in depth and receive an accompanying set of echoes, one spectrogram for the left and right ear. And similarly, as it rotates to different orientations at the same position, it will see something different and will receive these different echoes. Okay, so imagine capturing these kind of paired data between the audio and the visual anywhere in this environment. Now, before I get to the self-supervised feature learning, let me show you first a case study we did to see how much power rests within these echoes. And the idea is, first, can we predict from the echo response alone the depth map for the agent's egocentric view? Call this echo to depth. Furthermore, how would this compare if we were to instead learn a similar model for RGB to depth, which is the traditional way one would tackle monocular depth estimation? And finally, if we put these together, can we augment monocular depth estimation by using echoes? Okay, and we looked at these three models. Here I'm showing you just two examples of what you get if you try to do this prediction from RGB echo or RGB and echo to the depth map. And the ground truth you'll see is in that second column. Now, we do see that, yes, from echoes alone, there is a signal about the shape of the scene around this agent. Okay, and you can see that compared to the ground truth, it's certainly blurrier and less complete, but it's getting the main shapes of the space, which is what we expect to get from emitting sound and listening for the echoes. Furthermore, doing so with both RGB and echoes is stronger, measurably so, than using RGB alone. And in this example, gives you a hint of why, because here in the back of the room in the top left scene, there's a strong texture change from this slight lifted part of the back wall, and the RGB alone sees that as a strong depth change, whereas the RGB plus echo sees this more correctly as smooth, thanks to the complementary information from the sound. Now we've tested this on data, quantified all of the above, and we do see that, as you might expect, bringing both these modalities together is stronger for depth estimation. However, that's not our endpoint. That's just to see, what's this data holding for us for learning. The real idea here that we call visual echoes is to learn a visual representation that is aided by the sounds and echoes experienced during training only. And in particular, the objective we put forward for learning this is to require the visual representation to capture whether the sensed echoes and RGB view were congruent or not. So it looks like this. The agent has the RGB input. We'll learn a visual echo net for those visual features. The agent also has the echo response experienced with binaural sound from the left and right ears. But here, during training, the echoes that are received are going to be aligned with the visual stream or not. And if they are aligned, they'll be in the same orientation as the agent's current view. But if they're not, there'll be an echo that the agent would have heard had it been turned 90 degrees to the right, behind, or to the left. And so the self-supervisable task here is for the agent to learn whether the thing it's seeing is aligned in space with the thing it's hearing. And that we can cast as a four-way classification task to the directions you see on the right. Okay. So why would this be a good task for the agent to self-supervise? The idea is that if the agent is able to look at just RGB and get from the RGB whether the sound is in agreement with the shape of the scene, it means it's forced to pull out those elements of the shape of the scene, like the relative depth, in order to see if that agreement is present or not. Okay, so we take the visual model here, the visual echo net, as the visual encoder. So again, I stress that now at test time, we want to encode a new image, but we have no audio. And that this is where we leverage what was learned with audio now to handle images that don't. And just to give you an example, an NYU data set for depth estimation, here we're applying the model I just described using a state-of-the-art framework where we replace the backbone model with our pre-trained visual echoes net. And we get results like the ones you're seeing here that are much better than those you can get just learning from scratch with the same exact model. So that shows you transfer then from replica, the synthetic environment in which we learned, to real-world images in which this visual echo features is having a good impact. And furthermore, we've done this not just for monocular depth prediction, but also for other downstream tasks that can benefit from this pre-trained spatial encoding, like surface normal estimation and visual navigation. And in these cases, what we're seeing is that we're competitive or even better than the supervised, heavily supervised ImageNet or MIT indoor scene pre-trained models. Okay, so for the last few minutes of this talk, I'm going to shift gears from audiovisual navigation to tell you a preview about our new work on occupancy anticipation, which is for visual navigation. Here's the motivation. So in current state-of-the-art models for visual navigation, there you will often find, just as you saw in the model earlier in this talk, an occupancy map that encodes the spatial representation of where obstacles are on the ground for this agent. So it can start to build up a map of the environment and then plan through it. Now, the limitation that we see in these models is that the assumption is that the occupancy represented will be limited to those regions that were visibly detected. In other words, it's very literal. You see the depth map, you project it to the ground, and those are the places at which you know there are obstacles. Our key idea is to rethink this assumption and attempt to anticipate occupancy even in unseen regions. So if we have an agent like this one looking at the RGB ecocentric view shown in the center, as well as the depth shown just to the right, rather than restrict its map from that snapshot to only what would be visible from that depth map in the middle, we want to extrapolate and anticipate portions of the map that are predictable given the semantics in the RGB view, as well as the prior over how these occupancy maps are typically laid out. And this, if done well, will very much map what the ground truth occupancy would be, even though we haven't seen from the egocentric view all parts of that map. Now, why should this work? Well, this example gives you some intuitive sense. In this particular view, if you look at the RGB picture, there is a clear floor, wood floor, a corner of it visible, which suggests that more of the space in front of the agent may also be free space. Furthermore, just to the left, there's a hint of a hallway, and so that could allow, based on some learned prior, to anticipate that there is a hallway extending from it. And finally, seeing the wall just to the right of the agent may suggest that that wall is likely to continue, at least for some distance to the right. And these are exactly the kind of things we learn. I'm not going into details of the framework in this talk for time, but we have a model to learn how to predict these anticipated occupancy maps, and then we inject it in two ways. First, within the model to extrapolate the encoding of the current map, and second, as a reward to the agent during exploration, in which we give reward for moving to places in the unmapped environment at which the agent is able to achieve greater anticipation. You can think of this as a new way to get better coverage, where coverage is not limited to being able to see more, but it's saying coverage such that you are able to anticipate more. And in the end, this could allow to a more frugal use of the agent motion to get a fuller map. And we can see this happening in these qualitative examples for instantaneous occupancy maps that are predicted, with a baseline being the state-of-the-art active neural SLAM approach, ANF, which is limited to the visible occupancy map, and then you see our approach, occupancy anticipation, towards the right there. So we're getting fuller maps, and if we put this into play with the navigation policy itself, we'll see here in the center what the map looks like restricted to the visible map, or the current approach, and with our anticipated map on the right. For example, in that dining room, it could anticipate that the space behind the table was free and make the map fuller as a result. Similarly, in this example, the agent keeps navigating and sees just portions of the scene that hint at what probably other nearby portions are like, and so it more quickly is mapping it. Okay. We have applied this for exploration, and here are results from Gibson and Matterport 3D, where you're looking at the map accuracy and the vertical axis as a function of episode steps or time. And we can see that the intelligent anticipation that we're proposing leads to more efficient exploration. So better map in less time, and this is compared to both the ANS mapping as well as a view extrapolation baseline. And finally, in the Habitat Challenge this year for the point goal navigation task, the occupancy anticipation is among the top performers. And I'm showing here the final leaderboard for the public-facing site for the test standard set. Okay, so I will close here, and to summarize, this talk was about agents that can see and hear in order to understand their 3D environment. And I showed three new technical ideas. The first, we defined the challenge of audio goal as a new navigation challenge, as well as a simulation platform that allows experimenting with it. Second, we introduced a model based on audiovisual waypoints and an acoustic memory within an RL framework to try and address this new task. And third, we introduced an image feature learning called VisualEchoes that self-supervises a spatially informed feature from images alone. And at the closing here, I just gave a teaser about our work on occupancy anticipation, which is a top performer for this year's Habitat Challenge. We'll stop here, and thank you for watching, and I look forward to your comments and questions.
Thank you very much, Professor Grauman. And I believe there are quite a lot of applications based on the visual and audio and application, because right now you are presenting in the indoor scenes. I believe in outdoor scenes, for example, in the nighttime or something like a hidden objects in the, for example, insects, and we want to identify some objects hidden. That is also pretty helpful for even for the wife. Sorry, even for the for the deaf people, and that is very helpful as well. So I have some questions from the audience, and let's say the first question is, does the agent have to constantly hear the sound in order to reach the goal? And what about if some agent responds to a short but acute sound in this case?
So I didn't hear the last part of it. I heard the part about the sound could pause, but could you please repeat the second part of the question?
Oh, sure. Yeah. So whether the agent needs to constantly hear the sound in order to reach the goal. And the second question is, how could the agent respond to a short but very acute sound?
Okay. Yeah. So you're right. The tests we did are nearly constant sounds, as in every step it would receive a sound. However, experiments I didn't show, we've looked at time varying sounds where, for example, rather than the phone ringing, maybe music's playing. And so what makes that closer to the intermittent sounds is that, intensity will go down and up and the tone will change. So it's not a constant signal. And that is more challenging, but still we found quite well handled once we have the acoustic memory, because it helps to deal with this, create more invariance to those changes over time in the sound. Now, I do think that, the more briefly we hear the sound, for example, imagine you walk in the door, you hear the short noise, and then you're done with sound. Well, that reduces to kind of having that first snapshot of audio observation, and then from there, needing to rely only on the visual. So, I mean, the model still holds, but certainly it's a scenario that's harder in the sense you're not getting a constant reinforcement of the acoustic signal.
Okay, and the follow-up question would be, you mentioned for GPS, if GPS is available in the indoor environment, that is very good. And but if GPS has noise, that would be good to use the model and the visual audio model. And what about if some audio also has noise? And how to deal with this issue?
Yeah, it's something we're testing too. And I only briefly alluded it with that one result where we saw that the audio goal, was at a certain flat rate. And then if it dipped down maybe 2 points in SPL, this navigation metric, if there was a bad microphone, which was like 40 decibels signal to noise ratio. So again, in the latest model I showed today with like the waypoints and the acoustic memory, those ingredients are important for us handling this noise. And when we look at this as a function of the amount of audio noise, just like I showed you as a function of GPS noise, things are quite steady if we have the acoustic memory. And this is compared to our earlier model as well as that other model I was comparing with from the literature.
Okay. Another question from the audience, and one audience is wondering how you render audio for each location.
Yeah, so the rendering, in this case, it's all pre-computed, and just for ease of experimentation, which that means is like for every source and receiver location that you would like to be able to hear, you have done this audio ray tracing and collected after some number of bounces of the sounds what reaches the agent ears. And here it's ears as in binaural sound to microphones placed about this separation. And so so I think the question is like how to get it at a different position. You're kind of looking to that room impulse response function and then convolving it with the waveform you want to hear, like the phone or whatever. And now you'll receive that sound. You just need to specify where you want to hear it from and where you are as the agent.
So a follow-up question would be, if you are for example, in the indoor environment, and the material is wall, and what about if some materials there, for example, some materials may absorb some more sound, and some may reflect more sound. In this case, is there any experiment to show the difference? This
is actually captured in the simulation. And by the way, I should say we're making these simulations public so that others can kind of work on them and build on these results. But yeah, the transmission coefficients, et cetera, of the effects of materials on the sound propagation are in this simulator. So we think this is really a state-of-the-art capture of what the audio, to the extent in the simulation it can be achieved, what the audio will be like, respecting both geometry and materials.
Okay, and in general, maybe one more. We have one more time for one more question. And in general, for your audio and visual work, and I believe quite a lot of time that is very specific. That is something are very good for visual clues. Something are very good for the audio clues, or something is very good for the mixture or giving different weight. Do you have some insight and which scenario we should use which clue to navigate or to do the same depth estimation?
Right. Yeah, we're starting to get that sense. So we did a study that you could find, I think, in a video on our project page for this that I didn't show here, where we took the trained model with both cues and then start to ablate or corrupt one or the other, and then see the effects on the agent action selection. So you want to know what time points is it using one or both of these signals more heavily to make its own action choice. And you do see some interesting things. It's not just that both are good and contributing. Sometimes, visual dominates. You can imagine, like, if I don't know, if I'm walking forward and it's like a couch that's big enough to trip on, but maybe not big enough to alter the audio response significantly, then the visual would be a stronger decision maker and, counterparts for the audio as well. So yeah, we're trying to visualize this. You might, these figures that I referred to on the video might be a way to get a sense of that more fully.
Yeah, do you think it's good to extend to the outdoor environment, which has more noise in the environment, outdoor environment in this case?
Yeah, I think that's a great challenge. Now, if taking our literal approach over there, as far as audio simulation, I believe that's much more difficult because you're in open space and you're not getting these, you don't have the mesh. Maybe you don't have as good of a mesh or as complete as a mesh to get these. But yeah, worth considering whether in simulation or not. And I think definitely the directional cues, think of a self-driving car with the sounds around it, which people certainly want to exploit about, the ambulance coming by or other things. This would be helpful for the visual reasoning too.
Okay, great. Okay, thank you very much, Kristen Grauman again. And I believe there are quite a lot more questions in the YouTube, and just we are run out of time. So thank you again. And there are about 200 people listen to your talk, and it's just a representation. So thank you. Yeah.
Okay, thank you very much.
Thank you.
Appreciate it. Bye-bye.
Bye.